This is called, shut up, bird. This is called SimStructure. It's a program I wrote in 2000, 2001. It's a Windows program. It simulates masses and springs. Basically, doesn't have torque. It uses a Runkata 4.5 adaptive step size algorithm out of the book Numeric Recipes in C. So for computer nerds, it's kind of like an unsophisticated person makes a simulator that's Euler. This is like using an amateur uses bubble sort. This uses a better algorithm. Although I have my doubts as to what happens if you have a lot of objects. Anyway, basically, as I think about it, what it does is it's an adaptive step size, so it slows down when a critical event is happening, like rapid change. So, like if just if a comet is going around the sun, maybe it takes smaller steps when it's close. Now, the way it does that, the way an adaptive step size works, is Runkata, you might have heard of. There's a fourth order and a fifth order. And what they do is they do the calculation with the fifth order to, and they know it's more perfect or more accurate. So what they do is they compare the calculation with the fourth order to the calculation with the fifth order. And so what they can, let's pretend that they're starting to get a lot of error. They would know that because when they do the fourth order, they say, hey, the fourth order is not matching the fifth order. So they're getting a lot of error. So what they can do is adjust the step size. So you take smaller steps. Anyway, so that's the idea. But it occurs to me, what if you have, okay, so what that means is you take step size 10, and then you start taking 0.1. Okay, now what happens if you have a whole bunch of comets in the same system? Then one's going to be slowing down, and then you're going to be slowing down for another one, then you're going to be slowing down for another one. So I haven't studied this, but just from my thinking about it, that's what I think happens. Anyway, so it does masses and springs. Oh, let's do some fun. Let's do some stuff first. It has a ground. I did 2 dimensions. 3 dimensions would be well, just with 2 dimensions. There's a lot of wisdom, and a lot of people should choose 2-dimensional games. Imagine doing the ground in 3 dimensions. Making an interface in 3 dimensions, it's so what it has is it has the gravitational force. It has, you know, F equals m1 m2 g over r squared. At first I had imaginary units. Then I finally changed it over to real units. It has the electrostatic. It doesn't have electrodynamic. Collisions are done as springs with overlapping. It's like really high order springs. It's you know, when it comes to computer video games, you can be a monkey and just invent stuff. There's a certain anyway, some of this is, I studied viscosity. I tried to get the viscosity of the air correct. I read a physics problem which talked about a basketball. Anyway, you can okay, so it has buoyancy in water, and this, I was very proud of this in 2000, but now they have Grand Theft Auto and all that. Anyway, but here's the cool thing, that this is what makes it different from Grand Theft Auto. Okay, so, well, you can have, okay, so you can have guns and thrusters and let's see. So this is just masses and springs. Here's a gun. So I tried to make a anyway. Okay, well, it's a lot of fun. Here's what I did this originally because I didn't have control system. Robots are expensive with servos and stuff like that, so I wanted to do a simulator to get some experience. So this is what I wrote. Actually, as a matter of fact, one of my first what started this was you see this quite a bit. Okay, we're going to get rid of the water. We're going to get rid of the ground. Oh, let's see. Did I reset? Yeah. Okay. Let's just throw some more in there. So I'm going to add an electric charge to the particles. So I had a network that I wanted to draw, a computer network at Ticketmaster. I still have the DOS program, and so I just wanted to make a network map. And so what I did is a lot of people do. A lot of people. I did this in 1993. I have a different program we can run. Anyway, just to make a network map. Anyway, a lot of people have done that. There's lots and lots of people. So anyway, one time I tried to, this is not optimal for settling. You want to do a minimization problem instead of a real-time simulation if you want to get to for that problem. Anyway, but if okay, so we're going to make this is what mine can do that nobody else can do. I did this for control systems, so we'll be ambitious. So the help file, Microsoft discontinued the format. The whole reason the reason you get Microsoft is compatibility, and the little motherfuckers. So my help file would no longer compile. I would have to install my old Visual C6, and then something got corrupted, and I think, does this have the help file? Okay. I don't know if it's gonna. Oh shit. I don't. Oh well. Anyway, so there's no help, so nobody can use it. I made an interpreter, and what I did is it's basically C. So we're going to make it's sort of like C. This is an interpreter. TempleOS has a compiler, but this has an interpreter. Somebody's going to jump all over and I did an interpreter for Ticketmaster's report generator. So I have a lot of experience. I had done a couple interpreters before I did a compiler. All I did is inline the code, and that's how I got started compiling. Anyway, we could go into that. But anyway, so error equals, so we have P1, P2. We want the top, we want, this is a grid. I have to do this setting here real quick. Anyway, so this is 5, 10, 15, 20. Let's go to 25, 30. Let's go to 30 minus P1y. The different elements have attributes. So P1y. Then we'll say T1 thrust equals now K sub P. We'll do this. Oh, we might. We're going to make a PID controller. So the proportional gain is going to be, now this is the saturation thrust. You can abbreviate the, I could add that to my C language. You can abbreviate the members as long as they're not ambiguous. That's what Ticketmaster taught me. Anyway, so K sub P times error. In other words, I can either say SAT or SATURATION. Anyway, you can abbreviate the member as long as it's not ambiguous. That's a bad idea for wisdom. Anyway, okay, so we're going to say thrust equals saturation times proportional times error. We should use, okay. Okay, now I can come in here and disturb it. Okay, so now, okay, so it's oscillating. We should probably give it less gain. I'm just gonna let's give it, how about that? As you can see, it doesn't really get any better. So now we're going to say K sub D, not KD. This is, we're going to do with the derivative. Let's give it a minus 0.05. Okay, so we could make a variable, but I don't want to. KD times P1. Now there's a member called derivative of y. So why don't, this is less clear. Why don't we put the negative here? So as it starts gaining speed, we're going to subtract from the thrust. So as it gets faster, it stops thrusting as much. So I don't have enough. Okay, that's a lot better. Okay, so now what you learn, look at this. It's parked with some error. That's a little bit disappointing. So it has some steady state error. So what we have to do is case of I. I don't remember what ballpark. Okay, so there's a crazy thing called an integrator. Okay, so the adaptive step size run kata uses an array, a state. It uses a vector for the state, and what this integrator does is it creates a new element in the state vector. Okay, so we're starting to mix the controller and the plant, but anyway. So you can even make filters if you feel guilty about having too much response from your motor. You can cripple it or do other things. I don't know. Anyway, so so we want an integrator. So the way the integrator works is you just assign to it, and that integrates the expression. Now all of this happens over and over inside the loop for the simulation. The simulation has to interpolate. This kind of gets, there are situations where it's counterproductive. But anyway, so it's doing adaptive step size. So sometimes it's taking tiny steps, sometimes it's taking large steps. And if it is not real time on the second, then it interpolates to get the value. I think in my TempleOS, I put this integrator into I built it in to the operating system as a library kind of thing. I feel a little bit guilty because I don't like black boxes. That's kind of contrary to the whole spirit. But I had to indulge and put an integrator in there. So anyway, it interpolates. In TempleOS, I think it doesn't interpolate. I think it just does it correctly. Anyway, so the problem with one problem with this algorithm is you don't always go forward in time. With the run kata, sometimes you're checking ahead in time, sometimes you're backing up, and so it presents problems if you have a member that breaks. Well, sometimes you're looking into the future and sometimes you're not, and if you're interacting in real time and stuff, so jumping around with run kata with different times is kind of bad, but that's the way it works. So if you're making use of the run kata integrator in TempleOS, be warned that it doesn't step forward in time monotonically. I learned that word. Okay, so error. Okay, so now we want plus k sub I times I error. I was so proud of myself. I showed this program to Lockheed, and I tried to show it to my professor. I think I might have showed the DOS version. Nobody's interested, but anyway. So I went to Lockheed and I tried to show him. I think I visited my high school and I showed my old physics teacher. He wasn't. They had some software. So this makes it if it has an integrator, it's a type 1 system. and it has 0 steady state error. So we have it's going to integrate. See, what happens is the longer it has error, it builds up some corrective value to the thrust. So if it's overshooting, that's going to cause the thrust to, the longer that error is accumulating with a too high, it's going to integrate and get a positive, and so that's going to, I think we want negative. Wait, what do we want here? I should know this. Okay, so the error, if it's too positive, we want to back off. So I don't even know why this is not worse. That can't be right. Okay, it's got too much gain. Okay, it's integrating slowly, or maybe, I don't know what it, I think it has to be small. Let's go smaller. It was better. Let's give it more. I forgot where we're supposed to be. Damn, it's really fucked up. We should probably back off a little bit on this if we're doing this. When I first saw that, I thought it was terrible. But then I saw it happen on a real one. It's like, holy shit, they have the same problem I do. It's real. You think I'm kidding. Check this out. Check this out.
Every day, you're thankful for the ones you love. And every day, you promise to protect them. OFF is here to help with proven protection against mosquitoes. Trust our family to protect yours. SC Johnson, a family company.
Firing in 3, 2, 1.
Okay, those guys did it good. There's one that's not very good. I'm not kidding. There's one that does. Why can't I get 0 error? That's the whole purpose of this. Son of a bitch. Okay. Where are we supposed to be? What is the coordinate? Let's get rid of the line. Okay. So that one. Oh, let's drop it. Okay, there. So 15. Okay, so we want to make 0 steady state error. So let's see. More cowbell. Okay, so you can make plots. Let's see if we can do this. We're getting really fancy. So there's a signal, S error, and if you say S error equals error, now I'm never going to remember this. Plot. Oh, you have to say okay, well, isn't that special? Okay, well, this is a lot better. We can see what we're doing. So why is it integrate? What the is something broken? Was it better when I had the other sign? Oh, that is true. Wait, okay. So if you have positive error, oh, it's negative y. Oh, I just got it backward. That's kind of embarrassing. The only dignity I have is getting the sign correct, and I blew it. Okay, that's a lot better. And now we just crank it up and we get it. So a type 1 system has 0 steady state error when you have this. However, what if we say plus 10 times t, 15 plus 10 times t? Now we have a moving target. now we have to, so I made this crazy language where if you want to make a digital controller, you can say, you can put this means sample 0.1, do this operation 0.1 times at 0.1. This means do this operation at every second or 0.1 second. That's the so it adjusts. So it's only changing every second. It's only changing the control every second or every 0.1 seconds. Let's say 0.25. If you watch, it locks on it's only changing every 0.25. That looks weird. What the fuck is that? Okay, so the interesting thing, this @ symbol is supposed to be for when the screen is updated. This is like the time control. So then we say line, I call it desired Y. I think there's a more standard. Desired Y equals 15. Desired Y. Okay. So now we say plot this one. X, Y, X, Y. That's what we do. X, Y, X. X is P1 dot X minus 5, comma, desired Y, comma, P1 at X plus 5, desired Y, comma, red, comma, number, let's say 3. The number means pixels. Okay, so now we're tracking a moving target. And notice we have a steady state error. Well, guess what? A type 1 system has error with a ramp. So we have to integrate again and make it a type 2 system. I2 error equals I. Okay, and you can imagine how this works. Plus KI2. KI2. Oops, I didn't do that right. KI2. What? KI2 times I2 here. Okay, KI2 equals. What do you want to say? Okay, this is crazy difficult with a slow. So it overshoots, and now it's going to integrate and hopefully drive the error to 0. Now it's oscillating. Okay, so we have other tools in our, we don't have to adjust I2. We probably should. I don't know. You know, I don't remember the lesson on how to tune PIDs. I remember the lesson. I remember lag lead was supposed to be more sophisticated. So they give guidelines on how you do this. I wanted to build intuition, and I succeeded. Overshoot. And, oh, we're way over. When I was younger, I said, oh, only integrate when you have it close. That's kind of, you can, and only do a minimum and a maximum. There's a lot of ways to be kind of a monkey. Okay, I don't know if it's going to overshoot. It's going to. Oh, are we converging? Yes, we are converging on. Okay, let's just. My dog wants in my room. Okay, we overshot a lot. When you have that integrator term, you don't need as much. Oh, that's not the issue. You don't need as. We can actually get rid of this, or practically. I don't even know. That's just hurts you. Overshoot, back off. See, what happens is you integrate all that error and you get a big value, and now you have to correct it. Okay, let's just. Overshoot. No. Damn it. We're not even changing it. How come it's not changing? That's kind of weird. It's not even changing. Overshoot. Way overshoot. Okay. Sometimes. Oh, that made a difference. Don't overshoot. Okay, it's not. That's why you need to learn the math, because okay. So you can be a monkey all day. I know I can do better. Stop, stop, stop. No, 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 no. Oh, fuck. Okay. So that's lovely. Okay, so when you disturb it, okay, so now we want, so we have a thrust control, and now we want an angle. Angle error. Okay, so I was kind of dumb and made I got confused. This is embarrassing. I thought unwrap made more sense in my brain, but that's wrong. I called them bonds. I didn't like the word member. It was particles and bonds. Anyway, masses and springs. Anyway, bond. I made it heading. It's in degrees. Okay, so angle error. G1 angle equals, let's just say, array. Okay, I can tell you it's the wrong sign. Now let's do this. Okay, it's going to oscillate. Now, when you have control signals, they start getting coupled. Believe it or not, we cannot correct the angle unless we have thrust. If it's tipping over, sometimes anyway, you can get in a situation where, anyway, that's where it's not elegant. The theory's worthless, or it's just real world. As a matter of fact, when this stuff is immediately, it's non-linear. I was like, oh shit. Satellites are easy, I think. I think it's linear in space. In this, well, no, that's not quite true. Anyway, so now we have error. We want spin. This is in radians per second, and I happen to know you need a small value, 100th. Okay, now it's fighting to keep it from spinning. So there, we made it corrective. So now we can perturb it, and it corrects. It gets back on course. Now, one time, when I took the courses, they never talk about, well, what about what path does the rocket need to take? Well, that's algebra. As a matter of fact, it's really strange because you talk about driving the error to 0, but you actually have to plan what path it's going to take. One time I did like, what if you want to make a missile that hits the ground on a target? Well, you have to use the parabolic, the quadratic formula. Anyway, so it's kind of duh. But you never do that. So if we guess what? This is what the coolest sounding thing I heard was fuel slosh. And I came up with my own way to model fuel slosh. You know, the fuel in the tank is sloshing around. So that's how I model fuel slosh. Oh crap. I love nonlinear equations. Okay, so here's what we want to do. We want to say, this gets a little bit old, but anyway, error angle 2. So error angle 2, bond 2. So P1. Why? Let's see. So, let's see. Error. We probably don't want to pay much attention to it. This stuff gets weird because to correct you have to go the opposite direction, and sometimes that's only until it starts turning that direction, and then you go the other direction. It's really funny. Okay, there we have the thrust turned off. Dude, don't turn off the thrust. What are you doing? So, okay, well, I don't think we're going to get it much better. We can do bond 2 spin, but this gets, I don't think it's going to get any better. That was pretty good. I got lucky. Boom. Up. You're way off course. Okay, it's oscillating. I don't think it's coming out of that. Now how can we fix this? Well, we can more cowbell. Okay. Well, I think we've had as much fun as we can. So it can, uh-oh, let's see. Okay, so I think we have to turn those. No, those are probably okay. There's kind of an amateur child control that doesn't use the language. And the kids can kind of make stuff. So we're just going to make some other thrusters. Let's make it a nuke. Okay. So, charge radius, explosiveness. Okay, I totally made this up, but that's just what you gotta do. It's 1 ton. Okay, so you know what we need? I'll tell you what we need. First of all, let's make it park. How about 19? I want to park it in the air. Okay, it's kind of messed up. Let's. Okay, well we can. Oh, we destroyed our tracking target. Tracking particle. Okay, so track. That's what we track. Okay, I don't want these. What we're gonna do instead. We're going to do is we're going to make, oh, this is explosive. We're going to make a gun, a very, very high-speed gun. Okay. And G1 dot fire equal 1. Okay, now we can make Star Wars. When I was in, I went to school in Hanford, Washington, by the nuclear, where they made the bomb. They have the Richland bombers, where the mushroom. I went to grade school in Richland, Washington. This is the Richland bombers. They have a nuclear cloud as their emblem. The Richland bombers. They made the plutonium for the second bomb, Nagasaki. And in school, I was in the gifted program, and one of the things we talked about was hello? This is Terry. Yeah, it's Terry A. Oh, good. What's up? Yeah. Yeah. It's you can download it from my website. I'll show you how. Bye. So go to my website, TempleOS.org, type in files, and then you can download SimStructure.zip. It's a Windows program. So anyway, in the gifted program, we had this was during Reagan and the Star Wars, and I remember analyzing shooting down missiles. I said, no way, because I read an article and it said you can coat them you can make them spin so that the laser gets distributed. You can make them have a burn-off layer. You can make them hello? Anyway, okay, so we could make this trigger when it hits a certain height. Okay, we've had our fun. So I wanted to TempleOS. I wanted to make something better. So I built that in. Now you can, instead of the way it looked, this is still the basic. It's a better. I don't do the interpolation the same. It's a little better. You deal with masses and springs. It's actually not anyway. It's a lot harder to set this up. but you can make a program, and then you can, I just plotted the sprites on top of the positions. So this is shooting down an airplane. So anyway, if you want to play with open loop, I'll stop this. Okay, this is to teach the kids open loop. It's really hard. There, just, I don't know if open loop's the right word, just manual. So anyway, so that's my program.